I was asked about numbers 18 and 20 from the assignment that's due today. So these are rolling without slipping questions. So this ball is rolling down this 20-degree incline. It gives an angular velocity and an angular acceleration, and it asks for the velocity vector of the center and the acceleration vector of the center. Remember that the way that I defined the acceleration and velocity of the center is with a coordinate system that's rotated to be along the path, along the surface. So what I'm going to do is I'm going to calculate it in the red coordinate system, and then I'm going to re-express my answers in the one that it's asked for. You can do that component by component using trigonometry, or the people who are taking deform right now might think like, oh, this is a job for rotation matrices, and that's a much quicker way to do it if you're used to it. Okay. What we have is that in that red coordinate system, the velocity vector is equal to negative omega r 0. The radius of the ball is 0.05 meters. The angular velocity is, well, it says it's rolling down the incline. So the angular velocity is clockwise. At 20 radians per second. So that's negative of negative 20 times 0.050. And so that is just positive 10, I think. But that's in the red coordinate system. And then the acceleration, this is of the center. And then the acceleration of the center is negative alpha r. It says that the ball is speeding up. So do alpha and omega have the same sign or opposite signs? Same, yes, right. Your second guess was right. So negative of negative 15 times the radius of 0.050. So this should come out to be positive 0.750. Okay, so what we have is, if you think of, so now we're going to re-express it in the black coordinate system, in the given coordinate system. So you can think of it this way. Our coordinate system that we want is like this. The velocity vector is like, what's the angle, 20? Okay, my stupid computer. I have to live with this computer for like ever because they don't give computers with styluses anymore. Okay, so they're both going in this direction, where this angle is 20 degrees. And so you can figure out the components of something with a magnitude of 1 that's at this angle, and then figure out something with a magnitude of 0.75 at this angle, and that'll give you the components in the given coordinate system. Another way you can do it is rotation matrices. These are awesome. They come in handy so often. And we talk about them a lot in D-form, but not much here. So here's how it works. We have our vectors in a coordinate system like this. And we want to re-express them in a coordinate system like this. Okay. According to the right-hand rule, in order to go from the one on the left to the one on the right, we have to rotate positive 20 degrees about the z-axis. That's according to the right-hand rule. Okay. And so our rotation matrix is cosine of positive 20 degrees, sine of positive 20 degrees, negative sine of positive 20 degrees, cosine of positive 20 degrees, and then 0, 0, 0, 0, 1. Yep.
Can you explain why about this C, like when you do your right hand side and C?
Yeah. So in order to go from the left to the right, it's a rotation like this, right? Yes. And so that means your thumb is pointing this way, and with your X pointed this way and your Y pointed that way, positive Z has to go that way.
Okay, thank you.
Sure. Okay, so these come out to be 0.940, 0.342, 0, negative 0.342, 0.940, 0, 0, 0, 1. That's a rotation about the z-axis of positive 20 degrees. And so our, like, let's say our velocity vector in the new coordinate system is that Q matrix times our velocity vector in the old coordinate system. And that just comes out to be 0.940, negative 0.342.
On this page, we don't have to multiply it times the transpose.
Exactly. That's only for tensors. For vectors, you only do it, you have the matrix on the left and you only do it once.
Okay.
Yes. You're not in D form, right?
No.
Yeah. So that's the way we do it in D form.
That's another class.
Yeah, right. Yes.
So that one is always on the bottom right? Or is that
The one is always in the along the. Okay, so let me just write it down for the acceleration. So that would be this matrix Q times 0.7500. And so that would be 0.705, negative 0.25650. Okay, so for a rotation about the y-axis, for rotation of the coordinate system about y, your rotation matrix would be cosine of the angle, 0, negative sine of the angle, 0, 1, 0, sine of the angle, 0, cosine of the angle. And then for a rotation about the x-axis, this would be 1, 0, 0, 0, cosine of the angle, sine of the angle, 0, negative sine of the angle, cosine of the angle. So notice there is like a pattern if you look at the x and z. Whatever axis you're rotating about has a 1 in that diagonal position and zeros in the rest of the column and the rest of the row. And then you have cosine, sine, negative sine, cosine. Y almost follows that pattern, but the y-axis always has to be a little difficult. So it switches where the negative is on the signs. Really, like, to make use of this, to make it useful, you would just want to have this stuff programmed into your calculator. And if anyone's interested, I'd be happy to help you get that programmed in. There might even be under course information in D2L, there might be a list of programs to put this in. But when you're used to it, I mean, so me talking about it all, like doing it all in detail, we could have finished faster by just doing the trigonometry. But once you get used to rotation matrices and you have a program in your computer, it's just like instant, and you can view any vector you want in any coordinate system you want very quickly, you know. And as the people in DForm know, you can do that with stress tensors too, which can be helpful.
Can you go back down to the x?
Yeah.
So the one we use with the z-axis.
What?
The one we use.
Yeah, we were rotating about the z-axis because they were both in the plane, the xy plane. I used to do a lot of joint biomechanic calculations, and this stuff was, I mean, just constant, you know. We would know, like, basically, like, you would do a scan or whatever to know the properties of like a bone that you're tracking, you know, and you know where the lumps are and where it bulges out and where the muscles attach and whatever. But you know that in a coordinate system that's fixed to the bone. Okay. So as the body moves around, this coordinate system is constantly moving around. And so you take your knowledge of where the muscles are or whatever, and you apply rotation matrices based on where the limb is positioned. And then you can do all these calculations involving, you know, muscle forces and stuff. That's the stuff you have to do in any kind of robotics too. Okay, that is 18, and then 20. Okay, so we have a bike with a wheel diameter of 0.72 meters. It's moving at a constant speed. And one thing that you have to get used to is that the speed of the vehicle is the speed of the axle of the wheels. The center of the wheel is fixed to the rest of the body. So when it says that it has a constant speed of 8 meters per second, that means that this has a constant speed of 8 meters per second. Okay. What's the angular acceleration that we need? I'm going to use this coordinate system. What's the angular acceleration that we need for this to stop over a distance of 10 meters? The way I'm going to do this is I'm first going to calculate the translational acceleration I need of the center of the wheel, just using kinematics equations from physics 1. And then I'm going to relate that to an angular acceleration using the rolling without slipping stuff. So in order for the center of the wheel to stop in 10 meters, I'm going to use this equation that says 2a, I don't know what the format you used in your physics class is, but this is how I am used to it. So position like final minus position initial is equal to v final squared minus v initial squared. And I want to calculate the acceleration. P final minus P initial, this is what we want to be 10. V final is 0, V initial is 8. So we have 20A is equal to negative 64. And so A is equal to negative 3.2 meters per second squared.
That makes sense because the velocity is positive, the acceleration needed to slow it down.
Perfect. Yep. That's always worth thinking about. Yeah. So those have to be opposite signs so that it slows down. And now that we know this, now we can say that the acceleration of negative 3.20 is equal to negative alpha r 0. And so negative 3.2 is equal to negative 0.7. Oh, no. I did this yesterday when I was talking about this to James, too. Be careful with radii and diameters. This one says that the wheel has a diameter of 0.72. So the radius that we want is actually 0.36. Alpha, and then alpha is equal to 0.8 repeating radians per second squared. Okay, so does it make sense that the angular acceleration would be positive? Positive means counterclockwise. You can see that in order for this wheel to be moving to the right, it would have to have an angular velocity that's negative, that's clockwise. The angular acceleration is counterclockwise. And so those have opposite signs. It'll slow down, so that makes sense.
Can you scroll down, please?
Yep. One thing to be careful about is these rolling without slipping equations look very similar to, well, the acceleration rolling without slipping equation looks very similar to the tangential acceleration equation of circular motion from physics 1. And the velocity for rolling without slipping looks very similar to the formula for velocity of a point in circular motion. So don't let the boundary between those two topics get blurry in your head. That's a dangerous thing, you know. Only apply the rolling without slipping equations when you actually have an object that's rolling on a surface. And when you have circular motion, they are related, but it's not the same thing. Then you use the circular motion equations. Yep.
3.2 divided by 0.36 shouldn't be 0.8. Like 8.
3 point. Yes. Thank you. 8.8 repeating.
I was like, oh.
Yeah. That's the new math they teach in schools now. Okay. Any other homework questions? So now we're going back to particle kinetics. I just introduced it last time. I said that there's one equation of motion in particle kinetics. That's Newton's second law. And I said that you have to use an inertial coordinate system for Newton's second law. And our equation of motion says F net is equal to the mass times the acceleration of the center of mass. And F net means all the forces acting on a body, but remember that that all the forces acting on the body are equal to all the field forces acting on the body, plus all the forces acting at the boundary, which is a lucky thing because all the internal forces, that's a infinitely, that's a huge quagmire of forces and we can just ignore it. So we should all take a moment to be thankful about that. Okay, so the first thing I want to say is one thing to notice is if you want the net force acting on a body, not individual forces, if for some reason you just want to know what the net force is, you can do exactly what we did in particle kinematics. And then just multiply your acceleration by the mass. Okay, so let me go for a second back to D2L. So all of these problems that we did in particle kinematics, I think probably all of them at some point ask for the acceleration of the particle. And so I could make these kinetics problems by saying the thing has a mass of 0.15 kilograms or something. What's the net force acting? And then all you would be doing is taking the acceleration that you calculated and multiplying it by that mass. And that would give you the net force in newtons. Okay. So I think there are a few problems, daily problems that I'm going to assign that are like that. It's basically kinematics problems, and then you multiply by the acceleration by mass to get the net force. So that means I can ask chain rule type questions, relative motion type questions, all the stuff that we did in kinematics. I can ask for a net force, make you do all that stuff, and then the only difference is you multiply by a mass. Any questions about that? Probably. I don't know. I haven't written it yet. Usually I just the the way I figure out what's going to be on the test is I like at my office hours the day before the test, I see what questions people are asking, and then whatever people don't seem to understand at all, then that's what I put on the test.
What did you say? You said the chain rule and something else?
Relative motion, just if you go back to your notes from particle kinematics, you know, it's broken up into few topics. Like one is differential equations using the derivative relationships. One is chain rule. One is relative motion. What? Rotational. Like, oh, circular and spherical motion. Yep, that's right. So all that stuff, anything that I did in kinematics, I can just ask, I can give you the mass and ask for the net force on the body. Usually though, we're trying to calculate individual forces or use individual forces to figure out stuff about the motion. So remember that I talked about forces with unknown directions and forces with known directions. So there are going to be two forces we're going to deal with known directions. Contact forces. Those are pushing contact. And this is when we're ignoring any friction on the push. So frictionless. And then the second one is pulling contact, and we'll always think of that as happening with cables. And then there are two forces with unknown directions. Directions. Those are the force applied by a pin joint in 2D. Let's see. And second, the force applied by a ball and socket joint in 3D. So in 2D, you would represent it like this. You draw axes in whatever your coordinate directions are, and then you label this with whatever your variable vector name is. In 3D, you do the same, but you'd have to indicate a third direction too. So I'm going to start with pushing contact. We're going to go through that a little. Then I'll go to pulling contact from cables. So pushing contact. And this is frictionless. And the rule for a pushing contact, if something is pushing on your chosen body, the force is perpendicular to the surface of contact. And toward the chosen body. Okay. And this is very intuitive. Like imagine if you're wearing a coat with you're holding a cake inside your coat because it's raining or something, and someone pushes you. Which direction is the cake going to go? Towards your chest, you know. So for example, let's say that we have two bodies on rollers in contact with each other. And this one has a mass of 100 kilograms, and this one has a mass of 40 kilograms. And a 500 Newton force goes this way. Let's say we want to calculate first, what's the acceleration of the pair of carts? And second, what's the force vector applied to the 100 kilogram cart by the 40 kilogram cart? Okay, so we're going to do this calculation. Bless you. This is a sort of a typical example problem, example of something that I would ask you to do in the problems. You've done problems like this in Physics 1. By the way, using that double subscript notation that I introduced last time, how would you write this force? What we want is the force on the 100 kilogram cart by the 40. Okay.
Name them something, or do we just leave them as numbers?
You can name, I don't know. Yeah, either one's fine. Okay, so when I teach this in Physics 1, I say like, okay, to calculate the acceleration first, just isolate the whole thing as a single system. But I'm going to do it differently here just because we're going to assume that we can solve systems of equations easily enough that it's not really a concern. We're going to isolate the two things individually, and then we're going to solve it as a system of equations. Okay, so I'm going to first draw a free body diagram of the 40 kilogram cart. So here's my closed outline. There's a weight force down that's equal to 40 times 9.81. So that is 392.4 newtons. And now the only job we have left is to go around the boundary and look for contact forces where the surroundings are in contact with the boundary. One place is at the wheels. When we start talking about rigid bodies, we have to deal with the fact that these are actually two contact forces with the wheels. But for right now, everything we're treating is happening in a single location. So I'm going to lump these all into a single force, and I'm just going to call this N40, the normal force that's acting on the 40. And then if you keep going around, there's one other place. Oh, and notice how this, what I said here is this pushing force is always perpendicular to the surface toward the chosen body. So this normal force is perpendicular to the ground, from the ground towards the cart. So that makes sense. And now we go up here. There's another pushing force that's applied to the 40 by the 100. So the rule says perpendicular to the surface toward the chosen body, and I'll call that R. Yep.
So for these problems, or like with the free body diagram, with the like force equation is the mass times, or the center of mass?
Yeah.
Acceleration, should we be like directing everything towards like all these force vectors towards the center, or does it not matter? what we put up?
I don't tend to do that, but you're right that mathematically that's what we're doing.
Oh,
I mean, I think of it more as like, well, this is what the forces are really doing. So basically, there's nothing wrong about this. It's just that we're not going to take the next step and figure out what moments these forces are applying.
okay.
We'll get to that when we start talking about rigid bodies. So I think I would just get in the habit of applying those forces where they actually act now that I think about it. Like, why do this kind of problem differently than what we're going to do when we get to rigid bodies? Remember that the weight force has to act at the center of mass. Okay, so
Would there be a frictional force due to the normal force and movement? Like,
yeah, we're ignoring that. So unless we're going to ignore friction generally, unless I tell you differently. So this is it. And now we can go to Newton's second law. And we have a force of 0, negative 392.4, 0 and 40. Negative R, 0. And all that is equal to the mass times the acceleration. Do we know anything about the motion of this thing?
Not yet.
Yeah, we are gonna assume one thing about it. We're gonna assume that this isn't gonna sink into the surface or jump off the surface, and so everything is just gonna happen along the x-axis. So I'm gonna put this as A0. It's not too hard to look at it and figure out that the acceleration is going to be in the negative direction, but I'm just going to leave it as positive and let the math figure out the sign. So we get one thing from the y equation. We get that N40 is equal to 392.4. That's not going to end up helping us at all, but then go to the x equation and we get negative r is equal to 40a. And we can't solve that because that's one variable for two equations. But I am going to set that aside, and we're going to have to use this equation with what we get from the other body.
Are we always gonna just put acceleration positive or just?
Yeah, yes, you can always just treat it like it's positive and the sign will work out on its own. And now we'll go to a free body diagram of the 100 kilogram cart.
For the
Mhm.
force equals mass times acceleration, that 40, is that the?
That's the mass of that cart,
Oh,
of the chosen body.
oh,
And then we'll go to the 100 kilogram. There's a weight force down of 100 times 9.81, so that's 981. There's a pushing force up. That's N100. There's a 500 Newton force this way. And then there's the only other contact force is the force applied to the 100 by the 40. The rules say parallel to the perpendicular to the surface of contact toward the chosen body. And since this is a contact force between two bodies, and we're just switching what body we're looking at, these have to have the same magnitude. So this is from Newton's third law, that we know those have to be the same.
Is there specific reason why we call the unknown force R?
Reaction. That's what it stands for. So it's like it's not a force generator that's causing that. It's it's a reaction to whatever force is, you know. Okay, Newton's second law for this one says R0 plus negative 500 0 plus 0 and 100 plus 0 negative 981 is equal to the mass times the acceleration. And now what I'm going to assume is that these two things are going to move as a single unit. So whatever the acceleration is of the first one is going to be the acceleration of the second one. So I'm just going to represent it the same way.
Is it because they're touching each other?
Yeah. Yep. And so the first thing we see is that N100 is equal to 981. Again, that isn't going to help us get any of the questions that I asked you, but you can see that right away. And then from the x equation, you see R minus 500 is equal to 100A. And I'll call this equation 2 star. And we're going to solve equation 1 star and 2 star as a system for the two variables R and A. So the starred equations are two equations for the two variables R and A. Okay, so I'm going to take what we know from the 1 star equation, and I'm going to put it into the 2 star equation. From the 1 star equation, you can see that R is equal to negative 40A if you multiply both sides by negative 1. So plug negative 40A in for the R here, and you get negative 40A minus 500 is equal to 100A. And so negative 500 is equal to 140A. And so A is equal to negative 3.571 meters per second squared. Yes?
This is just an idea I'm thinking about. Now we have two objects. Can we treat them as one?
Mm-hmm. Yeah. And that's, yes. And that would let you do it without solving it as a system of equations. This class, though, is going to be about, there's no way around the fact that this class is going to end up being about solving big systems of equations. So we're just going to do it this way for now because that's how we're going to do it later.
This equation that we just have right now is essentially just the two masses and the forces, right?
That's right. Yep.
But this way it kind of gives us...
Yeah, so, right, this approach is trying to set us up for what's coming later. Yep.
So you mentioned you're going to be solving a lot of systems of equations. Would, like, putting reduced row echelon form?
Yes, and I'm going to talk about that today, actually. Yeah. Okay, and now, so we have A. Now we want to calculate R. What equations can we use to calculate R? Well, as long as we haven't made any mistakes, every equation that we have on here is true, is a valid equation. So just look for the place that gives it to you the easiest. I guess the easiest one would be R is equal to negative 40A. So R is equal to negative 40 times A, which now we know is 3.571. And so R is equal to about 142.85 newtons. Those are variable values, though. I asked for vector values. So how do we take these and give them as vector values? Well, the acceleration vectors of the two are the same. They're both a0, So we can think of the acceleration vector as a0. We already defined it that way. Now we just have to plug in the value for that variable a. So the acceleration vector is negative 3.571, 0. And now for R, we maybe have to be a little more careful. What force vector are we trying to find? There's no such thing as a force vector for the contact force between the two of them. You have to specify which body you want the force on. We want the force that's applied to the 100. So I'm going to go back to the free body diagram for the 100. And this is the force vector we want. And so the force on the 100 by the 40 is equal to 142.850.
Wait, can you show again which vector you look at?
Yeah. So the question asks for the force vector applied to the 100 by the 40. So we know we're going to look at the reaction force as it appears in the free body diagram of the 100. Okay, so I'm going to skip the free body diagram of the 40 and Newton's second law for the 40, go down to the 100. This is the force we want. And this is how we represented it. And so now, like, this is the force on the 100 by the 40. We just didn't know what R was yet. Now we can plug the R value into this vector, and it gives us the thing.
So from looking at that free body diagram, really what you're telling for the R vector is just which direction it goes?
Yeah.
The magnitudes are the same?
Right.
Okay.
Yep. And so now, what if it had asked for the force vector on the 40 by the 100? Yeah, exactly. Newton's third law says that if you switch the order of the subscripts, you just switch the signs of the components. So this is negative 142.85. So the next type of force that has a known direction for us is pulling contacts. And we're always going to think of that as being applied by cables. And the rule for the direction of this force is parallel to the cable. Away from the chosen body. The pushing force was toward the chosen body. Pulling force is away from the chosen body. So like, for example, if you have a cable connecting an object to the ceiling, then a free body diagram of this object would look like this. Coming from the center, you have 20 times 9.81, so that's 196.2 newtons. And then we're told that this is 50 newtons. And the only other place that there's contact is where the cable attaches. So that force is parallel to the cable, away from the chosen body, and I'll give it the label capital T for tension. You would to do a calculation, yeah. I'm not going to calculate this one. I'm going to do a different one. Okay, so one thing to notice here, this is going to be really important to us. For any ideal, I'll put that in parentheses, cable, that touches nothing between endpoints except possibly again in parentheses ideal pulleys, the magnitude of the force of that tension force is the same anywhere along the length of the pulley. I mean along the cable, not along the pulley, anywhere along the cable. Okay, so what is an ideal cable, and what is an ideal pulley? An ideal cable just is massless. So usually in engineering applications, the weight of a cable is small compared to the forces that it withstands. And so in a lot of applications, leaving out the mass of the cable, you get good results. For an ideal pulley, we're going to assume that it has no mass and no friction. Okay, really it's the main thing isn't the mass, it's the moment of inertia. We'll talk about that later. And later in the class, we'll see how a calculation would change if you didn't have an ideal pulley. Because pulleys do have mass, they do have a finite radius, there is friction. How would those things go into changing all this? But for now, we're assuming that those pulleys, all they do is transmit pulling forces, convert them into different directions. Okay, so let's do an example problem. So this is kind of Dr. Seuss looking, but it's just to make the point that these pulleys don't do anything but change the direction of forces. So let's say we have a rolling cart here. And this has a mass of 10 kilograms. And then there's a pulley there. And a pulley there. And then a pulley up here on the ceiling. They're supposed to be round. And this cable goes like, whoops, I did that one wrong. Okay, so this cable goes like this, and then over this pulley, and then up to that one, and then down. And there's a body here that has a mass of 5 kilograms. We're going to assume that each of these like stretches of cable is either horizontal or vertical. And let's say we want to calculate the acceleration vector of the rolling cart. And we want to calculate the tension in the cable. So first I'm going to do a free body diagram of the 10 kilogram. Uh, 10 times 9.81 is 98.1. There's a pushing force from the surface onto the wheels. I'll call that N. And then that cable is pulling on the right end. The rule says parallel to the cable, away from the body. And then that's a complete free body diagram. And so now I'll put this into Newton's second law. We got 0, negative 98.1, plus 0n, plus positive t0 is equal to the mass of 10 times the acceleration. And we're going to assume that this thing isn't sinking or jumping off the ground. So we're going to just assume that the acceleration has a x component. And I'll just write that as a0. And if it comes out negative, it'll do that in the math. All I have to do is figure out a coordinate axis that it moves along. That's all I have to, that's my only concern there. The y equation tells us that n is equal to 98.1. That's not going to come into anything. And the x equation says t is equal to 10a. And we can't solve this yet because it's one equation for 2 variables. So I'll just put a sticky note on it and set it aside. And then I'll go to the 5 kilogram. So there's the body. The weight force is 5 times 9.81, so 49.05 newtons down. And the cable force, okay, the direction we know is parallel to the cable, away from the body. What about the magnitude? Well, since all this cable does is cross through ideal pulleys, we know that it has the same magnitude T as the force on the other body. So this force is parallel to the cable, away from the body, and we know it has that same magnitude T. no other contact with the surroundings. So now we can go to Newton's second law. And it says 0t plus 0, negative 49.05 is equal to the mass times the acceleration vector. Okay, the acceleration, the free body diagrams tell us everything about the left side of this equation. They don't tell us anything about the right side of the equation. But is there anything that we can know from this configuration about the acceleration of the 5?
Going up and down.
It's going up and down, that's right. And then we also have to have the proper sign relationship. We don't have to know which way this system is moving, but basically you can always think of it like this. If that first body moves an inch in the positive x direction, where does this body go? An inch where? Down. And so if I call this one A0 for the acceleration, I have to call the acceleration of this one 0, negative A, because of that inch down thing, okay? And it can get a little messier than that, even with certain configurations of pulleys. We'll talk about that later, but you can see this one, I think it's pretty clear intuitively that an inch of this going this way equals an inch of this going down. Okay, so I'm going to write this as 0. So this is 0, negative A.
Wait, but that does positive A.
So we could I could have done this one first, okay? And then I would have written this as 0, positive A. But then when we got to the second one, I would have written this as negative A, 0, because what matters is the relationship between their motions. And we'd end up with the same answers either way
So
in the final.
if we have the first one positive A, the next one, the other object should be negative.
Yeah, in this case, that's how it works. But you have to think about it, how it works for each individual problem like this. Okay, so here we get an equation that says t minus 49.05 is equal to negative 5a. And that's my equation 2 star. And now I'll plug what I know from 1 star into 2 star. And we get 10a minus 49.05 is equal to negative 5a. And so 15a is equal to 49.05. And so A is 3.27. Then you can go to that 1 star equation, and T is equal to 10 times A. And so that is 32.70 newtons. The last thing is this problem asks specifically for an acceleration vector, not just a value of a variable. And so to get the acceleration vector of the rolling cart, well, we've already specified that this is the acceleration vector of the rolling cart. And so now you just take that A value and plug it in. And so what we get is 3.270 meters per second squared. Any questions about that?
Can you show again the vector that we did?
Yeah. So, in Newton's second law, we always have to specify an acceleration. Sometimes we know something about it, sometimes we don't. Here we knew a little bit about it, and that narrowed down what it could be. But we always have we have an expression for the acceleration vector. We just don't know what the variable a is yet. So now once we find what that variable a is, we can plug it into this thing, and now we know completely what the acceleration vector is.
Yeah, and then for t, you just use the one.
Yeah, just any equation that you want. As long as you haven't made any math mistakes, any equation on here is valid. So I could have used equation 2 star, but equation 1 star was a little simpler, so I used that. They'll give the same answer. Yep.
So when plugging like the equation 1 star and the equation 2 star, and you're getting that answer for your acceleration,
Mhm.
How do you keep it straight, like what that acceleration is referring to? Like,
Yeah, so all that is, really in a way, don't think of that as an acceleration. Like I could have given it any variable name I wanted. I could have just called it X or something, But what we're really doing is just solving a system of equations for a variable. It only is related to the acceleration through this expression in Newton's second law.
oh wait, is the acceleration between the two bodies always the same?
Well, in this case, not always, but in this case, the magnitude is the same and the directions are different.
Okay.
But you have to just sort of think about that geometrically for each problem. I'll do an example next time where it's sort of like this, but one of these things only moves half as much as the other one, Yes?
So then you asked for T and cable, would we have to put that also in vector form, or could we just?
I just asked for T, and I didn't ask for a vector, so that's okay. But I could have asked for what's the force vector that the cable applies to the 5 kilogram cart, say. And then you would have to go to, now this is the force vector that the cable applies, and you'd plug that T value in there. Yes?
Will the number of pulleys make it different if we have more pulleys?
It will, for one thing, it will affect the number of equations that you have in your system of equations, because you're going to have to isolate each one of those bodies. So if there's 100 bodies, you're going to have Newton's second law 100 times. But that's too much drawing, so I won't make you do that.
So like for example, on this one, if you just added like another pulley in between the top and bottom that you had, it wouldn't affect anything.
It wouldn't affect anything. Yeah, isn't that funny? Yeah, it wouldn't affect anything. And I could have just gone, it would have been easy to make this problem, cut out that one on the bottom, and yeah, it doesn't affect anything. Or even just cut out both of these 2 pulleys on the right and just have the 5 on the cable hanging over the first one, and it would be exactly the same.
So you can just add as many ideal pulleys as you want to the system and not change anything?
Exactly, yeah. Yeah.
So
The only thing that changes from a pulley is the direction of the force. So, yeah.
So here we're not looking at like the, how we used to isolate the body with the pulley?
In statics, we did that. Yeah.
Like the pulley was part of the body?
Right.
Would that make it easier for finding T?
Yeah. Well, we did that. I can think of one example where we did that, and it was because the pulley was attached to the body, and it was just thinking about how many variables would be introduced. But in this case, those pulleys are not attached to the body. So, but actually, when we talk about blocks and tackle, however you say it, we will include the we will have cases where the pulley will be lumped in with the rest of the body. So, any other questions? Okay, well, these were both just two equations for two variables. That's easy to do by hand, but we're going to get much bigger systems of equations eventually. And so you're going to want a more systematic way to do it, or in a faster way than substitution. So this is the way to solve big systems of equations. Come on. And I think it's true that all of your calculators have this on it. So your calculator will just do these for you. Big systems of equations. This is reduced row echelon form. And I think all your calculators have it referred to as RREF, just the so I'm going to do it with an example of like, here's my system, x minus 2y plus z is equal to 50. X minus y minus z is equal to negative 20. And 3x plus 2y is equal to 10. And so the first step is make an augmented matrix. And so you're just going to choose an order for the variables. And you're just going to be consistent with that through the whole thing. And those are going to be your columns of your matrix. This matrix is always going to have a number of rows equal to the number of equations you have, and a number of columns that's one more than the number of equations you have. And so I guess most people would probably choose the order to be X, then Y, then Z, but we wouldn't have to do it that way. And then the last column is for the constants. And the rows represent equation 1, equation 2, and equation 3. And now we're just going to give the coefficients of the variables in the spots. So for equation 1, my x has a coefficient of 1. My y has a coefficient of negative 2. Z has a coefficient of 1. And the constant is 50. And it's very important that the constants are alone on the other side of the equations. And all the variables are together on their side. So the second equation, x, we have 1. Y, we have negative 1. Z, we have negative 1. Constant is negative 20. Equation 3, x's, we have 3. Y, we have 2. Z, we have 0. Constant, we have 10. When you get those big systems, you would never want to solve 12 equations for 12 variables by substitution, but it's really just as fast here as it would be for 2 equations. So contact me if you have trouble figuring out how to find that on your calculator or anything. But eventually we're going to be using that all the time. For now, you could solve what we're doing by substitution for now, but eventually you're going to want this. Yeah,
So the 6.9 is x, the negative 5.4 is y, and the 13.
exactly. Yep. So this is x, y, z. Yep. And I could have done this as z, y, x, and the coefficients would have switched orders, and then they would have come out as z, y, x going down from the top. Okay, that's all.